Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous video, we introduced measurement error, the gap between the variable we observe and the true value we wanted to measure. But there's an important distinction we need to make before going further. Not all measurement errors behave in the same way. So the type of error matters just as much as the size of it. A simple example, let's suppose we want to measure someone's true weight, okay? And for a moment, let's suppose that true weight is actually 70 kilograms. And you use 3 different scales, and one of them gives you 69.8, and the other gives you 70.2, and the other 70.1, and one more gives you 69.9 kilograms, and so on. Are these errors systematic? And the answer is no. They fluctuate around the truth, sometimes too high, sometimes too low, but on average, they are right. Okay, this is the best case scenario of measurement error, random noise that cancels out across observations. And most econometric theory starts here. Now, we have what we call classical measurement error. Okay. The example that I just gave you actually is a classical measurement error problem. Its key characteristics are randomness, which means there's no consistent direction. It is centered around the true value. Okay, so on average, you're making 0 error, and you are equally likely to overestimate or underestimate. Okay. Now, keep in mind, you can have a true value somewhere here, and then you have observed values. They are all scattered around it, okay? As you can see, there's not a single direction we're going to. It's completely random noise around a signal. They don't push estimates consistently in any direction. Now, what I want you to remember, though, is that classical measurement error, as we're calling it here, doesn't mean old-fashioned. It means the error satisfies a specific mathematical condition. Okay, so in here, we're assuming that on average, the error is equal to 0, or that the covariance between your x and the error is equal to 0. Okay, now we'll use these properties when we derive the consequences in a later video. Another everyday example is how many hours did you study last week? So last week's study hours. And you could ask students, and sometimes you could have someone who says 18 instead of 20, someone who says 22 instead of 20. And you could have someone that says 19 again instead of 20. These are honest mistakes. Some overestimate, some underestimate. On average, they roughly cancel out. So again, this is classical measurement error in action. But what happens when from a classical measurement error, we turn into a non-classical measurement error? In this case, suppose that you are asking people to report their income on a survey. And let's also assume for now that true income is 50,000. Okay. And You ask people, but most people deliberately or unconsciously underreport what they earn. So someone would say 45K and the other would say 43K and someone else might say 46K and so on. So as you can see here, the error points all in the same direction. We are underestimating it, which means that nobody overreports and the mistakes are not random. The mistakes are systematic. This is non-classical measurement error. And the key difference is classical errors average to zero across the sample. Non-classical errors do not. There is persistent direction to the mistake. You can think of other real-world examples, for instance, self-reported weight, self-reported height, tax returns, hours worked, drug or alcohol use, political opinions. So these are all cases where respondents will give reports that they think it's okay. And in each of these cases, the error has consistent direction. It doesn't average out across the sample. So there's a tendency to give answers that make someone look good or pitiful or so on. So if we were to make a comparison between classical and non-classical measurement error, this is what the summary would look like. In terms of direction, classical error gives you a random, no consistent direction, while non-classical error, measurement error, is systematic, so there is a present direction. For average error is 0 for the classical one and non-zero for non-classical. In terms of effects on estimates, it would mean that for classical, there is going to be noise, and non-classical is going to be actual bias. Which of the two is easier to handle? Well, classical is easier to handle. Non-classical, it has its own challenges. But why does this matter for econometrics? So econometric theory typically starts by assuming classical measurement error. So we'd be in this column right here, because it is like well understood and it has mathematically tractable consequences. But in practice, many real data sets contain non-classical errors, so deliberate misreporting, rounding, and so on. And when errors are non-classical, the standard result no longer apply. The analysis becomes harder to do and the solutions become much less reliable. This is why researchers spend considerable effort validating their data, comparing survey responses to administrative records, for example, or to assess whether errors are classical or systematic. Because remember, the type of error determines the severity of the problem. In this video, we showed, once again, classical measurement error, which has a randomness to it and it averages to 0, versus non-classical or systematic measurement error, which has a direction and it's persistent, and the distinction determines how serious the consequences are and whether standard fixes apply. In the next video, we'll study the first important case, so what happens when measurement error is in the dependent variable y. The answer here might surprise you, so stay tuned and I'll see you in the next video.